Hello. So what we are going to do is finding the fraction of atoms on the surface of a nanotube or a nanomaterial. So from what we've done in class, we were dealing with cylinders. So finding the fraction of atoms on the surface of a nanotube which is cylindrical in nature. So the first thing to do is you calculate the entire volume of the cylinder or the nanotube. Then you calculate the volume per atom. That is the volume of one atom in the cylinder or the nanotube. Then you obtain the radius and diameter per each atom. That's the same as the radius of one atom that you've calculated. Then you obtain the number of atoms on the curved surface of the cylinder or the nanotube. Then you obtain the number of atoms on the top and bottom of the surfaces. Then you calculate the number of atoms on the surface of the nanotube. Then you obtain the number of atoms in the entire volume of the cylinder or the nanotube. Then you divide the number of atoms on the surface by the number of atoms in the entire volume of the cylinder or nanotube to obtain the fraction of atoms on the surface. Okay, so let's use this pen here for example. So let's see, this is a cylindrical nanotube. What we are saying is, first of all, calculate the entire volume of the cylinder. So let's assume this is a perfect cylinder. Here is perfect, and then the bottom here is also perfect. Okay, it's also like perfect, like this place. So we are first of all going to calculate the volume of the entire cylinder. So we find the total volume of this cylinder. Then we calculate the volume per atom. So to calculate the volume per atom, there's a formula that you can use to do that easily. Then you obtain the radius and diameter. So the atom that you've calculated, atoms are spherical in nature. So if we know the volume of the atom and we know the formula for the volume of a sphere, we can relate them to find the radius of the atom. And once we know the radius, you can definitely find the diameter. Okay. Then you obtain the number of atoms on the curved surface. So if this is our cylinder, this is the top surface, this is the bottom. We are assuming the bottom is like the top. Okay, it's not pointed like this, it's also curved. It's also like this part. And then the curved surface is this part where they've written the big pen, whatever. The curved surface is where I'm rolling the curved surface. That's the curved surface. So you obtain the number of atoms on the curved surface. So the curved surface is from the edges here, okay, all over this the curved surface. Then you obtain the number of atoms on the top and bottom surface. So since the top surface is the same as the bottom surface, okay, like for a cylinder, the top surface is identical to the bottom surface, we can find the number of atoms on the top surface and also find the number of atoms on the bottom surface. Then we are saying calculate the total number of atoms on the surface. So once we found the number of atoms on the curved surface and the top surface and the bottom surface, when we add them, we now get the total number of atoms on the surface of the whole cylinder. The total number of atoms on the surface of the whole cylinder. Then you obtain the number of atoms in the entire volume of the cylinder or nanotube. So after we've done that, now we calculate the number of atoms in the whole volume of this nanotube or cylindrical nanotube. Then you divide the total number of atoms on the surface by the number of atoms on the entire volume of the cylinder or nanotube to obtain the fraction of atoms on the surface. Okay, so that was an introduction to what we are going to do. So we have a question here. This was given by Prof. Jansen in class. For a 100 nanometer long and 20 nanometer diameter silver nanotube cylinder, find the following given the atomic diameter is 0.288 nanometers and density of silver is 10.49 gram per centimeters cube, and the molecular weight of silver is 107.9 gram per mole. So they've given us this data and they're asking us to find the surface area to volume ratio, that's A, and then B is the aspect ratio, and C is the fraction of atoms on the surface. So what we are doing is fraction of atoms on the surface. So we are just going to jump straight to that. All right. So we're given the length of the silver nanotube to be 100 nanometers, the diameter to be 20 nanometers, the density to be 10.49 gram per centimeters cube, the molecular weight, okay, the molecular weight is represented by A. Sometimes they call it molecular weight, sometimes they call it atomic weight, so it's basically the same thing. To be 107.9 gram per mole. And then another information you need is the Avogadro's constant. That's represented by Na. Sometimes they say L, but then since we have L here representing the length of the nanotube, we are going to use Na, which also means the same thing as Avogadro's constant. And that's 6.023 times 10 to the power 23, I think, atoms per mole. So I don't really know if this constant will be given, but if it's not given, you should have it in mind. Avogadro's constant 6.023 times 10 to the power 23 atoms per mole. All right, so let's go step by step. The first step is calculate the entire volume of the cylinder or nanotube. So since it's cylindrical, we know the volume of a cylinder is pi r squared each, okay? But in this case, we are using L. So it's like you have a cylinder like this. Let's say like this, a cylinder like this. So it's not drawn to scale, okay? So not drawn to scale. So you have a cylinder like this. This is the height of the cylinder, okay? We can also say this is the length of the cylinder. So we can replace this H here by the length L. This is the diameter of the cylinder, okay? This is the diameter of the cylinder, and half of the diameter of the cylinder should give us what? The radius of the cylinder. Now, in this case, we were given radius instead of, the formula here is radius, but then in our question we were given diameter, so we can go ahead and use the diameter, or we can divide the diameter into 2 to obtain the radius and then fix it here. Anyhow you go about it will do. So you can write this as pi r squared L, or if you want to go with the diameter that was given in the question straight away, then you can do pi d squared L over 4. Okay, this is the same thing. So I'm going to take my pi to be 3.142. So I have 3.142 times d. The d was given as 20 nanometers. So 20 squared times L, which was given as 100. 100 all over 4. So I'll do the calculation. 3.142 times 20 squared times 100 over 4. And I have the volume of the entire cylindrical nanotube to be 31420, because it's volume nanometers cube. Okay. The next thing is calculate the volume per atom. That is the volume of one atom in the cylinder. So this is the second one. So there is a relation or a formula that you have to know to be able to go about this. Okay, we have, I think that's step 2. So we have this formula. Density is equal to Na over Vna. This way, rho is density, N is the number of atoms, A is the atomic or molecular weight, V is the volume, and then Na is the Avogadro's constant. So we can manipulate this formula to obtain the volume per atom. Volume per atom is the volume of one atom in the whole cylinder. So when we do that manipulation, we have our formula to be V over N to be equal to A over density times Avogadro's constant. So it's like you have a big volume and you know the number of atoms in that volume. Okay, so if you want to find the volume of one atom in that volume, you just divide the total volume by the number of atoms in that volume and you get the volume per atom. So we say this is what we call the per volume per atom, right? So let's find the volume per atom. We know A to be 107.9 gram per mole, and we know all over root with 10.49 gram per centimeters cube times Avogadro's constant is 6.023 times 10 to the power 23 atoms per mole. Okay, so this grams will cancel this grams, and then this mole will cancel this mole. So let's find what we have. We have 107.9 over 10.49 times 6.023 times 10 to the power 23. And we have V over N to be 1.7078. I'm approximating it times 10 to the power negative 23. This is per centimeters cube, so it will move up, and then we have centimeters cube, and this is atom. When it moves up, we have per atoms. Now, we cannot testify that we are working at the nanoscale, so it means you have to convert the centimeters cube to nanometers cube. Okay, we have to convert centimeters cube to nanometers cube. We can do this straight away by the relation 1 centimeters equal to 10 to the power 7 nanometers. Okay, now we are working in the cube, so we can cube everything here and cube everything here, cube everything here. So therefore we have 1 centimeters cube equal to, this is 10 to the power 7 cube, so that 7 times 3 will multiply, so you have 10 to the power 21 and then nanometers cube. Okay, so this is just like a short way of going about it. So we are just going to replace this centimeters cube here by this, and then we are done. So you have V/N, which is the volume per atom, so 1.7078 times 10 to the power negative 23 times. Now, instead of writing this centimeters cube, we are going to write this because this is equal to this. So you are going to have 10 to the power 21 nanometers cube per atom. Okay. Now, we can simplify what we've done further to 1.7078 times 10 to the power